Hi, I'm Ryan Baker, and this is Big Day in Education. Today we're going to discuss the deep knowledge tracing family of algorithms. Our story starts with DKT, Deep Knowledge Tracing, by Chris Peach and his colleagues. Deep knowledge tracing is based on long, short-term memory networks, and it fits on a sequence of student performance across skills, predicting performance on future items within the system. Like all neural networks of its sort, it can fit very complex functions, very complex relationships between items over time. So our story begins with a little bit of a drama, because the initial paper, and actually an initial press release published even before the paper was submitted, reported massively better performance than original BKT or PFA. And in fact, the difference was so big that it seemed at first too good to be true, and it was. Xiaolu Shang and his colleagues reported that Peach et al. Had used the same data points for both the training and test, which, as you should know by this point in the course, is a massive sin. Following on that work, Kaja and his colleagues compared DKT to modern extensions to BKT on the same dataset and found that it was particularly beneficial to refit the item skill mappings. Kevin Wilson and his colleagues compared DKT to temporal IRT on the same dataset, and the bottom line was that all three approaches appeared to perform comparably well. At the time, curmudgeons like me said, this DKT stuff, not going to do anything. But it turned out to be the beginning of what could be called DKT family algorithms, a range of knowledge tracing algorithms based on different variants on deep learning. And at this point, there's now literally hundreds of published variants. Most of them tiny little tweaks to get tiny little gains in performance. But in aggregate across the hundreds of publications, there appears to be some real improvements to predictive performance. There was a comparison between various DKT family variants and more classical algorithms, for example, in Gervais et al. 2020, that showed pretty conclusively that DKT family really is getting better performance. In the next slides, I'm going to discuss some of the key issues that researchers have tried to address in these improvements to DKT and what their approaches were. One of the first problems noted for DKT was work by Jung and Jung, who reported degenerate behavior for DKT. And we talked a little about degeneracy for BKT and PFA, but this degeneracy was even worse. People getting answers right and the knowledge estimates dropping. Wild swings in probability estimates in short periods of time, like a student gets it right and they go from 30% probability of knowing it to 95%. They get it wrong, they shoot back down to 20%. Now, these issues really kind of raise questions about whether DKT could actually be used in the real world, because we can't have these kind of behaviors in a real system being used by students. But Jung and Jung proposed adding two types of regularization to modulate these swings, increasing the weight of the current prediction for future prediction and reducing the amount the model's allowed to change future estimates. And those regularization steps actually made a big difference in already making DKT, just with their first extension, DKT Plus, a much more realistic algorithm for real-world use. Another limitation that people pointed out with DKT was that the DKT family is impossible to interpret in terms of skills. The DKT family predicts individual item correctness and not skills. So what do you do for entirely new items? BKT or PFA, because they treat item within skill as essentially interchangeable, with a beta parameter in PFA that you can set to default, they can gracefully handle new items. DKT at first couldn't. So what do you do for entirely new items? And what information can you provide teachers who don't want to know that a student is going to get this item right and this item wrong, but what knowledge the student has in an interpretable fashion? The first attempt to address this problem comes from Zhang et al., Jung's group again, who proposed an extension to DKT called DKVMN that fits an item skill mapping too. It was based on a memory-augmented neural network that keeps an external memory matrix that neurons update and refer back to. And this produced not just estimates of correctness, but also latent skills. But, unfortunately, the latent skills that it auto-generated turned out to be very difficult to interpret. Li and Jung, 2019, same Jung, proposed an alternative to DKT called KQN that attempted to output more interpretable latent skill estimates, again fitting an external memory network to fit skills. At this point, also attempting to fit the amount of information transfer between skills, which might remind you of Sao Pedro's work from the previous lecture. But it turned out that it still just wasn't all that interpretable. Scruggs et al. Proposed a different way of extending DKT family. They proposed an extension that could be applied to any DKT family algorithm, where they used a human-derived skill item mapping, and they took all the items mapped to a skill and averaged their performance. So it's very crude. This extension just averaged performance on all items, including both unseen and already seen items, the predicted performance at the time. It turned out that these averaged estimates, despite being a fairly crude method, and I can call it a crude method because I was a co-author on it, led to successful prediction of post-tests outside the learning system. So it was actually capturing something latent about student knowledge that could be adapted to new items involving the same skills in a different setting. Now, Scruggs' extension, because it was so simple, is almost certainly not the final word on this, but what it shows is that we can now really get to estimates of latent knowledge that are predictive of new items on the same skills. And what I think that tells us is that we are now on the road to being able to use DKT family for a lot of the same purposes that BKT and PFA were originally used, to get interpretable skill estimates. Another area of concern that people have raised is, what is DKT really learning? And Ding and Larson demonstrated theoretically that a lot of what DKT learns is actually just how good a student is overall. Zhang et al. Followed this up with empirical work showing that most of the improvement in performance for DKVMN is actually in the first attempt on a new skill. So that really kind of corresponds to Ding and Larson's finding that it's really about how good the student is. More broadly, that benefit, and you can see on this graph here, dissipates mostly by the second practice attempt on a skill. In particular, there's essentially no benefit to deep learning after several attempts on the skill, which is about the point where students often reach mastery if they didn't already know the skill. So a lot of what DKT is doing is not helping us assess whether a student has reached mastery during their practice in an online learning system, but just what skills they probably already knew to begin with. Now, beyond these issues that people have tried to address, people have also just tried to make DKT better. And one of the important variants on this is called SACT by Pandey and Karipas, who proposed a DKT variant that fits attentional weights between exercises and more explicitly predicts performance on the current exercise from performance on related past exercises. This gets a little bit better fit, but it doubles down a little bit more on some limitations we've already discussed. Ghosh et al. Also proposed a DKT variant called AKT, which explicitly stores and uses the learner's entire past practice history for each prediction, using an exponential decay curve to downweight past actions, and using a Roche model embedding to calculate item difficulty. And unshockingly, this does better because it's now using additional information. It's using the time sequence. Building on that general paradigm of adding in more information, Saint Plus by Shin et al. Added elapsed time and lag time as additional inputs, leading to better performance. And adding in more information still, ProcessBERT added timing and use of resources like a calculator, finding that this further additional information led to better performance. Now, in discussing these, I've tried to be fairly calm about how big the benefits were, but there's actually a curious methodological note that I kind of have to report, which is that most DKT family papers report not tiny improvements, but large improvements over previous algorithms, including other DKT family algorithms. And those improvements somehow seem to mostly or entirely dissipate in the next paper. And what's going on here? Poor validation and overfitting, unfortunately. A lot of DKT family papers don't use student-level cross-validation, which, my gosh, why didn't they watch Big Data in Education? Poor cross-validation benefits DKT family algorithms more than other algorithms because DKT family fits more aggressively. So, in other words, a lot of the gigantic improvements that we see in individual DKT papers are because the authors are literally using data from a student's future to predict their past. Also, almost as troubling, a lot of DKT family papers fit their own hyperparameters for their current new algorithm, but use past hyperparameters for other algorithms, which of course is going to massively bias in favor of their new one because they've got more flexibility of fit. Having said that, despite the shoddy evaluation in a lot of DKT family papers, there have been solid evaluations of them, and those have typically demonstrated that there are benefits to DKT. My current favorite, even though it's like now 3 years old, is Gervais et al., who compares a bundle of KT algorithms on several datasets. And I love that not only were their methods solid, but that they looked across a whole lot of datasets. Some of their key findings. Different datasets have different winners. A surprising number of DKT family papers are on a single dataset, and Gervais et al. Find that that's going to always lead to kind of getting an idiosyncratic winner. They also found that the DKT family algorithms perform better than other algorithms on large datasets, but worse on smaller datasets. And in particular, DKT family algorithms perform worse than the LKT family on datasets with very high numbers of practices per skill, such as language learning domains. They do find that DKT family algorithms are better at predicting if the exact order of the items matters, which can occur if items within a skill vary a lot. And they find that DKT family algorithms reach past performance faster than other algorithms, which corresponds also to the Zhang et al. Findings I mentioned a few minutes ago. The DKT family work is moving so quickly. There's literally dozens of papers a year. And I think that one of the key frontiers for this family of algorithms is getting beyond correctness. Ghosh et al. Propose option tracing, which extends the output layer of the neural network to predict not only correctness, but which multiple choice item the student will select. And that has a lot of potential for being able to capture misconceptions as well as correct knowledge. Open-ended knowledge tracing, Liu et al.'s work, goes even beyond that in integrating KT with a GPT-2 model that's fine-tuned on 2.1 million Java code exercises and written descriptions of them in order to generate predicted specific code which will make predicted specific errors, helping to get at not just what a student knows, but what they don't know and what misconceptions they have. So, work is continuing. Dozens of recent papers trying to get better results by adjusting the deep learning framework in various ways. There's a lot of potential here to get better results. This kind of reminds me of the kind of thrash we saw in the past on natural language processing and on things like boosting algorithms that really led to very powerful results. I think we're seeing the same thing happening here. What this means is that this lecture is going to be out of date almost from the moment you see it, and you'll probably be seeing an updated version not too long from now. So next up, and last up I think for our KT week, memory algorithms.